All right, hello everybody. In this video, we're going to be going over question 3 on this week's worksheet, which is covering minimum spanning trees. So the question is, suppose you want to design a telephone network connecting all the cities labeled A to G in the neighborhood. We'd like to do so at the least cost. And so this is a very realistic example of when we might want to create a minimum spanning tree. As you can see, the weights of all these different edges is presumably the cost of creating that connection. And so of course, in order to minimize cost, we'd want to create a minimum spanning tree. So starting with part A, in a graph with n vertices and m edges, how many edges form a minimum spanning tree? Well, a minimum spanning tree is a subset of the tree class, right? And if we remember, by definition, a tree that has n vertices is going to have n minus 1 edges. Let's take a moment to kind of convince ourselves of the fact, right? So if we have a tree with one vertice, well, obviously it will have 0 edges, right? Then if we want to add one vertice, it's now going to have 1 edge and 2 vertices. And if we add another one, we're going to have 3 vertices and 2 edges. And this property holds true even no matter where we put this new vertice. As you can see here, this has 4 vertices and 3 edges. And so overall, this is going to have n minus 1 edges or 6 edges in the above graph because we have 7 vertices total. Now, part B, will the new graph contain any cycles? Describe its structure. All right, and once again, by definition, the graph is a tree, right? And trees contain no cycles. Now, there are 2 specific subsets of trees that we're kind of interested in looking at, right? A tree can be any combination of vertices and edges that fulfill the properties of a tree, right? But there is another unique subset of the tree class, which is a spanning tree. A spanning tree is a tree that exists inside of this graph, but that it touches every single vertex in the graph, right? So for example, if we had A, B, C, and then edges A, B, and AC, that would be a tree, but it would not be a spanning tree. In order to have a spanning tree, it needs to touch all 7 of these vertices. In addition to that, there is a subset of the spanning trees, which is the minimum spanning tree, which is what we're really interested in looking at. It is a spanning tree that minimizes the total weights of all the edges of the tree. All right, now on to part C. Now we know 2 different ways to create minimum spanning trees. There's Kruskall's algorithm and Prim's algorithms, but starting off, we're going to be looking at Kruskall's algorithm, right? And here are all the steps. So I'd highly recommend trying to solve this for yourself first by running Kruskall's algorithm and finding the minimum spanning tree. All right, now that you've tried it for yourself, let's come back together and work on it together. The first step is going to be to sort all the edges by increasing order of their weight, and I've done so right here. So for example, BC has weight 1, and FG has weight 8, so it is all the way over here. Now notice, because there are numerical ties, Kruskall's algorithm does not actually care. I mean, it does matter, but either way, you're going to have a valid minimum spanning tree, no matter what order you put them in. So for example, on BC and EF here, they both have weight 1, but having EF first and BC first would still generate a valid minimum spanning tree. Then we're going to pick the smallest edge and check to see if it forms a cycle with the spanning tree so far. If it doesn't form a cycle, we're going to add this edge to the tree, and we're going to repeat this step until there are V minus 1 edges in the spanning tree, where V is the number of vertices in the graph, right? So now, starting with BC, if we add BC to our minimum spanning tree, well, because there's literally nothing in our minimum spanning tree right now, that will obviously not create a cycle, so we can go ahead and add BC. Then EF, if we're going to add to our minimum spanning tree, which currently contains B and C and the edge BC, well, adding EF is also not going to cause any problems, so we can go ahead and add that. Then CD, similarly, is not going to create a cycle, so we can add that. Then CF is also not going to create a cycle, as you can tell, so we can add that. Then AB will still not create any cycles. And now AD is going to create a cycle, right? Because if we add AD, then ADCB is a cycle. And so we're going to skip AD. Then DF will also create a cycle because of DCF. Then CE will also create a cycle because CEF. And then finally, EG is not going to create a cycle, so we can go ahead and add that. And now notice, look how many edges we have. We have 1, 2, 3, 4, 5, 6 edges. And 6 is V minus 1 because we have 7 vertices total. And so now Kruskall's algorithm terminates, and we have constructed a minimum spanning tree like this, right? And that's kind of generally how Kruskall's algorithm works. Now, we also know how to do Prim's algorithm. However, Prim's algorithm is not required for you, but as an optional exercise, I would highly recommend trying to use Prim's algorithm to solve this. Now, if you use Prim's algorithm starting with C as your start node, then you'll actually end up with a graph that is exactly like this. So if you want a bit of a challenge, you can go ahead and do that for yourself. In terms of applying Kruskall's and Prim's on the test, I think most of the time the questions involving these algorithms will be just simply applying them to a minimum spanning tree. So as long as you memorize how each of those work, you should be pretty much set in terms of these topics.